So, we're talking about a new chapter today. We spent a lot of time talking about moving objects, but now we're going to discuss objects that stay still. And one example of objects that stay still are objects that are in equilibrium. So, what equilibrium actually means is that the momenta, both linear and angular, are constant. So if you remember Newton's first law, objects at rest stay at rest, objects in motion stay in motion unless acted upon by an outside force. Okay, that's what we're talking about here. So objects that are moving with a constant momentum, be it angular or linear, are actually in equilibrium. We are, for this chapter, mostly considering objects in which these are going to be equal to 0. Okay? And that means when these are equal to 0 that we are talking about static equilibrium. And if you go off to engineering school, you may very well take a class in statics. If you go off to architecture school, you may very well take a class in statics. So, there's usually paper under there. It's not lined. If you want lined paper, that top left drawer of mine has paper like we were using yesterday. Okay? Take whatever. Or there's scratch paper. Okay. So these could also just be equal to constants, and then we would have objects that were moving in equilibrium. But in this chapter, we are concerned with static equilibrium. So again, we can talk about stable equilibrium, and unstable equilibrium. Just like we did when we were talking about potential energy curves. So in stable equilibrium, remember that a perturbation, I don't really want to write it that way. Let's put it this way, that even after a disturbance, the object returns to equilibrium. Okay. And remember, that was being in the bottom of the bowl. Okay, that we gave it a little push and it might have gone up, but the force brought it back. And that for unstable equilibrium, after a small disturbance, object does not return to equilibrium. So this is great and all that, but it doesn't really help me figure out when something is in equilibrium. And it doesn't really help me figure out what conditions I need to meet to put something into equilibrium. So let's talk about that. So if I know that the momentum of my object is equal to a constant, then what's dp dt going to be? 0. And if dp dt is equal to 0, what else is equal to 0? What's dp dt equal to? It is in fact F net. So that tells me that for an object in equilibrium, F net, all three directions of F net are going to be equal to 0. if the angular momentum is equal to a constant, what's dl dt going to be equal to? 0. Which tells me that what else is going to be equal to 0? Yeah. Now, I told you that whenever you talked about torque or angular momentum, you always had to specify an axis. Have I specified an axis over there? No. That means that the net torque has to be equal to 0 around all axes. So these really infinite number of equations, you get 3 out of here, and as many torque equations as you can find axes, are the criteria or the conditions that must be met for equilibrium. So let's try a problem. Let's do page 345, number 6. Most of the things that we are talking about will be in stable static equilibrium, but it actually is just for equilibrium. It depends on some other things, whether it's stable or unstable. All right, somebody read us the problem, please. Okay, so we are back in the realm where it is incredibly important to draw a picture. In fact, we're going to be drawing multiple pictures. So I have this scaffolding, which is basically just a platform that has cable or rope at either end. And it's something that painters or window washers do. And while it doesn't really matter in this problem, there are usually pulleys attached to the cables, and you pull the cable and you have one person on either side and they pull the cable and the platform goes up or the platform goes down. Okay, so I've got my scaffold here, or my platform, and it's 5 meters long, and it's got some mass that we'll call little m. And then I've got a window washer. We'll call that mass big M. And the window washer is 1.5 meters from one end. It doesn't really matter which end. And I know some things. I know big M is what, 80? I know little m is 60. And what am I supposed to find? So we'll call them T1 and T2. We'll come back to axes in a minute. Okay. So I want to find forces. How do I find forces? Okay, so if I'm going to use F net equals ma, what do I have to have first? I need to have a free body diagram. Okay, so I'm going to draw a free body diagram for the scaffold because that's what my T1 and T2 act on. Okay, so here's my scaffold, mass little m. What kind of forces are acting on my scaffold? What? There's a gravitational force. Now, it matters where that gravitational force acts. So, it actually acts at the center of gravity. In most of the world, nothing. The center of gravity is where the gravitational force acts by definition. If you are in a uniform gravitational field, which you pretty much are right now, okay, because all parts of you, all parts of the scaffolding are being pulled on by the earth at the same rate, then we say that the center of gravity is the same thing as the center of mass. However, if you were in a rapidly changing gravitational field, such as the area around a black hole, then your center of gravity may not necessarily be at your center of mass. Because if I went feet first into a black hole, the pull at my feet would be very different than the pull at my head. And spaghettification is the technical term. Not for the person that's going through it for eternity. It is. So then the center of gravity may be somewhere else, probably I would say lower, as opposed, yeah, spaghettification. It's a technical term. Yeah, like a spaghetti because you get stretched out. And eventually everything pulls apart. But it would be honestly an eternity of pain, much like being dissolved in the Sarlacc pit. So I'm not really sure that's the way to go because of the way of the time dilation and everything. True, but you'd never get to tell anybody about it. No, you can do it on your own. And actually, Neil deGrasse Tyson has a wonderful essay about it that I'll copy for you if you ask me. But right now we're doing this, okay? So that's one force that's on my scaffold. What else? What other force? Okay, so I got my tensions. It doesn't really matter which is which because they didn't tell me. I'm just going to make them that way. What else? The force from the person, the window washer, whatever it is. Okay? How is that person interacting with the scaffolding? Yeah, and so what are they, how is that force? Ultimately, but the gravitational force is between the window washer and the earth. What's the force between the window washer and the scaffolding? Yeah, but what's that force? What are we going to call that force? It's a normal force. Okay, so it is in fact, how do I label it? Yeah. It's the normal force from the window washer. Because that's the third law pair. If you were thinking about the window washer, the normal force would be the force of the scaffolding on the window washer. So hang on. So the third law pair is going to be the force of the window washer on the scaffolding. So yeah, that's about where he is. Oh, I'm not worried about this vertical thickness here. I mean, if it makes you happy, I can extend it all the way up to there. It does to some degree, but the scaffolding isn't thick enough that's going to make a difference. Okay, and then as Zoe said, this is in fact going to be equal to the gravitational force of the window washer. Because if you make the window washer's free body diagram, gravitational force pulls down, that's canceled out by the force of the scaffolding on the window washer. Okay. So is this object moving? Nope. So what do I know for sure? What? F net is 0. Okay. It is in equilibrium. P is equal to 0. All good things. So remember that this F net equals 0 is really 3 equations, right? F net x is 0, F net y is 0, F net z is 0. So I'm going to let up be positive y just because I got to pick something. And what direction am I going to sum my forces in? Y, because it's the only direction I have forces in. So F net y is going to be equal to 0. Put a little s on there for scaffolding. And so I've got T1 plus T2 plus FG window washer plus FG scaffolding, and those all have to sum up to 0. Well, that's an excellent question. Let's keep going and see if we can figure out the answer. Okay, what's my next step here? Put in the signs. Okay, so tension 1, positive or negative? Tension 2, positive or negative? FGW. FGS. So basically I've got the T1 plus T2 is mg plus mg. Which leads me to a problem. Because how many unknowns do I have? How many equations do I have? So what do I need? I need another equation. Now normally we might go to the x direction. Do I have forces in the x direction? Do I have forces in the z direction? No, so I'm not going to be able to use that to figure it out. What else do I know about equilibrium though? I know that the angular what? I know the angular momentum is 0, which means what else is 0? Tau net is 0. Now remember, tau net is 0 around any and every axis of rotation. So you get to pick. A really good idea for picking is a place where you have an unknown. Because, oh, well, I can't put my axis of rotation in a particular direction. I can put it in a particular place. So for instance, I'm going to put my axis of rotation here. It is extremely important that you label the axis of rotation. It would also be nice if you wrote above tau net equals 0 about axis of rot at left end of scaffold or something else equally descriptive so that I know where your axis of rotation is. Okay. And then you have to write down all the things that can have torques. So for instance, T1 will have a torque. What else will have a torque? I'm writing down everything that could possibly have a torque, and then we'll go back and get rid of things. Okay, what else is going to have a torque? What else is going to have a torque? Okay, I'm just going to call it GW, gravitational force due to the... And what else is going to have a torque? Yeah, the gravitational force on the scaffold itself, and that's all got to equal 0. Now we can make some more space. I just want to be able to see the picture. Okay. Actually, we're still going to need the picture. Because remember, do you get to choose which way is positive or negative when you're dealing with torques? No, which way is positive? Counterclockwise. Remember, when you're trying to figure out if a torque is positive or negative, think about it as a string that pulls whatever your object is around that axis of rotation. So let's talk about the torque due to T1 for a minute. What's that going to be? Where is T1 acting? On the axis of rotation, which means its moment arm is, which means the torque is. So now I don't have that torque anymore. So T2, again, the force goes this way. It's going to pull my board in the positive direction. How about the torque due to the gravitational force on the washer? I'm going to pull it this way, right? Which is going to be negative. And how about the torque due to the gravitational force on the scaffolding? Negative. So again, what I get is the torque due to tension 2 is going to be equal to the torque due to the gravitational force on the window washer plus the torque due to the gravitational force on the scaffolding. Yeah, because my next question was going to be, how do I find what a torque is again? Okay. So, well, what is R? Okay, so for T2, what's that distance? 5 meters, right? The length of the scaffold. So this is going to give me 5 times T2 times the sine of what? 90 degrees, because they're perpendicular. Okay. The gravitational force due to the window washer, what's that R value going to be? 1.5, right? Because he's standing 1.5 meters from the edge. Okay. So that's going to be 1.5. The force is mg, and again, it's the sine of, because they're perpendicular. How about for the gravitational force due to the scaffolding? What's that distance going to be? 2.5 meters. This is the only situation in which I will not get upset if you don't use units, because there's just way too much stuff running around here. So make sure everything is in SI units before you start. And what's the angle again between them? 90. No, it's thin enough. That's what I said before, why it doesn't really matter. If it was a larger object, yes. But if you've ever seen a scaffolding, it's about as thick as a ladder. It's not going to make a difference. So this gives me 5T2 is equal to 1.5 capital mg plus 2.5 little mg. And like heck, I know all that stuff, right? So what's T2? How many sig figs we got running around here? So let's see what other people get. Okay. What's up, Maddie? No. No. This is back where I've already taken any SIGN sign into account, and G is just 9.8. Okay, so that was pretty cool. So now we need to go back and figure out what T1 is. But we have an equation up here, right? Where T1 plus T2 was big mg plus little mg. And so T1 is going to be big mg plus little mg minus T2. And again, what are we going to get? Sig figs? Is that what other people got? Yes? Okay. All right. So, couple things. Number one, Zoe, did we answer your question? Did we figure out how to take into account the fact that those forces were not all really acting on the same dot, that they were spread out over an object? And the answer is yeah, that the torque takes that into consideration, because the torque is a measure not only of what the magnitude of the force is, but how far it's acting from the axis of rotation. Another thing, if I had instead put my axis of rotation over here, what would have happened? Well, the torque due to T2 would have been equal to 0. And what would I have ended up solving for? T1. So did I actually need to do any of this? No, I could have just applied tau net equals 0 twice in 2 different places and never done anything with F net. Now this was somewhat simplified because I only had 2 unknowns, but we'll do a problem tomorrow that'll be a little more complicated. Okay, so I am going to let you go because we can't do the whole problem. But who's going to participate tomorrow in the thing? Yuzo? Okay, and Maddie. All right. So like I said, I will stop class for that time, but I expect you to respect to offer me the respect that I am offering you, in that you'll go directly there and come directly back, so that we only have to stop class for like 20 minutes. Okay? And I think we'll finish this chapter on Thursday. Okay? Seriously. You've read all you have to read. Yeah, we're done. We are done. See ya.